Acids and bases definitions. This particular problem gives you some practice identifying which is an Arrhenius, Bronsted-Lowry, or Lewis acid and base. Now, primarily what we use here in organic chemistry is the Lewis definition. However, it is important to retain this knowledge from general chemistry. Now, the Arrhenius acid and base definitions, as described above, an Arrhenius acid will increase the concentration of hydrogen, and a base, when dissolved in water, will increase the concentration of OH. So both of the Arrhenius definitions involve aqueous solutions. Therefore, all of this stuff that's gases and solids, that doesn't qualify for the Arrhenius definition. So I'm just going to move those over to neither right now. So what we have is KOH and H2SO4. We have potassium hydroxide, which is an Arrhenius base. When dissolved in water, it increases the OH concentration, and sulfuric acid, when dissolved in water, increases the H concentration. Now, the Bronsted-Lowry concept of acids and bases. Now, that involves transferring a proton. So Bronsted-Lowrys can lose a proton, and Bronsted-Lowry bases gain that proton. So what we need to do is look at what happens in our equation. So here we have HS minus, and that is going to gain a proton. And because it gains a proton, that is a Bronsted-Lowry base. That means that the water must be donating a proton, and it is the Bronsted-Lowry acid. In this case, no protons are being transferred. Therefore, that is not a Bronsted-Lowry acid nor base. Now, a Lewis acid and base involves the transferring of an electron, of a pair of electrons. So in this case, the water is going to be donating an electron pair to the aluminum. So the aluminum is receiving that electron pair, and it is the acid. Water is the base. In this equation, the lone pair on the nitrogen is donating to the bromine. And because the bromine is accepting, it is the Lewis acid. Acids and bases predicting the position of equilibrium. Well, what we're going to do is compare our structure on the right with the structure on the left. And remember that a conjugate acid has one more hydrogen than its base. A conjugate base has one less hydrogen. So what we're comparing is the hydrogen content. So for this particular example, we have one more hydrogen. Therefore, this is a conjugate acid. And over here, we have one less hydrogen. That's a conjugate base. Here is one more hydrogen, conjugate acid, and here is one less. So we have a conjugate base. This structure also has one less hydrogen than the structure on the left, therefore it is a conjugate base. Part B, we're going to draw the structures of the conjugate acid and conjugate base of this reaction. So what we have here is hydronium, and hydronium always wants to donate its electron. It's not happy. So this hydrogen is going to come over here to this structure. So I'm going to start by dropping a nitrogen on my pad of paper here, or screen, and then attach my methyl group. Now, Mastering Chemistry doesn't like it when your atoms are out of the box or even touching the box, so I'm going to move that in. And then I'm going to move these hydrogens and add one to it. Now I'm also going to declare the formal charge on nitrogen here. And then I have to draw my water molecule and show that it has lost a hydrogen. Now I'm going to ignore the lone pairs here. Part C, we're going to predict the position of equilibrium of an acid-base reaction, and we're going to be using our pKa values. Now, the important part for predicting whether or not you're going to favor reactants or products is right here. We're going to compare the pKa values of the acid on the left with the pKa values of the acid on the right. So the larger the pKa value, that's where the arrow will point. We will point towards the larger value, and if the larger value is on the reactant side, we're going to favor reactants. If the larger value is on the product side, then we will favor products. So what I'm looking at here, I'm looking at phenol as my acid with a pKa value of 10. And then on the product side, I have water as my acid, and it has a pKa value of 15.7. Because 15.7 is greater than 10, I'm favoring my products. So for this reaction, I have the hydronium ion, which has a pKa value of -1.7, And then I have my piperidinium ion, which has a pKa value of 11.2. Because 11.2 is much greater than negative 1.7, products are favored in this reaction. So for this reaction, I have water, and then I also have dichloroacetic acid. Now what happens is the dichloroacetic acid is going to be donating its proton, and it gives it up for water that turns into hydronium. So what I'm comparing is 1.35 and a negative 1.7, and because 1.35 is greater than negative 1.7, reactants are favored. Same idea with the phosphoric acid, pKa value of 2.5. Water is accepting the hydrogen here, so water is acting as a base. So I have phosphoric acid of 2.15, hydronium on the other side at negative 1.7. 2.15 is greater than negative 1.7, therefore reactants are favored.